Hello and welcome to our webinar PID Control Made Easy. My name is Turevsky. I'm in Technical Marketing at MassWorks. Today I hope to show you how easy it is to design and implement PID controllers with MATLAB and Simulink. Because I will be talking about MATLAB and Simulink, the first thing that I'd like to do is show you the final product. Let me switch to Simulink and show you the model of closed-loop engine control. There is a subsystem called engine that implements engine dynamics, and there is a subsystem called my controller that implements the controller. Let me go inside of that subsystem, and here you see a discrete time PID controller block. If I run the simulation, you will see that this block operates on fixed point signals. That's because we will implement this PID controller on a fixed point microprocessor. And so let me switch to MATLAB and show you C code that I automatically generated from this PID controller block. You see the PID gains defined here and the actual PID algorithm implemented in the few lines of code here. You see that this is the fixed point code, very compact, very efficient, suitable for implementation on a fixed point microprocessor. I will spend the rest of the webinar explaining how we actually got here. Now that we've seen the final product, let's step back and do a little primer on PID control. PID stands for Proportional Integral Derivative. Here's a picture of PID controller from Wikipedia. The green box here represents the process that we're trying to control. It could be the engine, it could be a chemical process or something else. The error signal is the difference between the set point that we want our process to follow and the measured process output. The PID controller operates on the error signal. The proportional term is the proportional gain Kp times the error signal. The integral term is the integral gain Ki times the integral of the error signal. And the derivative term is the derivative gain Kd times the derivative of the error signal. We add all those terms together to get the requested actuator value. Now, why do we need these three different terms? To see that, let's go back to MATLAB. I prepared a little script that will show us why we need the three different terms. In the script, we'll start with defining a simple transfer function that you see here. Let's execute this cell. This transfer function is a very simple second-order transfer function with 0.2 second time delay. Let's first play a step input through this transfer function. And the blue line here is the reference signal, and the green line is open loop step response. We see it's not quite getting to the desired value. So let's design a PID controller, and let's start with simply proportional controller, because we are trying to understand what the different PID terms do. Let's start with a simple gain of 3. Using commands from Control System Toolbox, we compute closed loop step response and plot it here in the red line. We see that it's closer to the desired value, but it's not quite there, and it's faster. What about changing the proportional gain? Let's try increasing it. So let's change it to 4, 5, 6, 7. As I press this button, you see the calculations are repeated and the results are plotted in the plot. You see that we're getting closer to the steady state value, but at the expense of the controller stability. It gets more oscillations. So instead of increasing the proportional gain, let's keep the proportional gain at 3 and add the integral term to our controller. Let's execute the cell, plot the results. And what we see here is the open loop step response in green line, proportional only controller in red line, and PI controller in the slight blue or cyan line. So as we see, it gets to the steady state value of 1, but it has a little bit of an oscillation going on. So to fix that, we can use a derivative term, which, as we will see, adds stability. So let's add the derivative gain to our controller and plot the step response for the full PID controller. Let's maximize this so we can see better. And now we see that the full PID controller gives us fast response. It gets to the steady state value of 1, just as we want, and it's more stable than PI controller. So that's why we need the 3 terms in the PID controller. So if PID control is all about tuning the 3 gains, that must be pretty simple. We could just write some C code, connect it to our hardware, and start running our hardware and tuning the gains, right? Well, unfortunately, it's not as easy. If you have unstable plant, this trial and error process is not going to work very well. You can actually damage the hardware and endanger the people. You also need to make the logic a little more complicated, for example, to protect against integrator windup. That's a condition that can happen when the actuator, when fully open or fully closed, doesn't still get you all the way to the desired set point. In this case, the error signal is a constant positive or negative value, and you will keep integrating it in the integral term. And as a result, when you change the set point value, the integral term is all wound up, so it will take it a long time to unwind. To protect against that, people use integrator anti-windup. A lot of time people do the tuning based on their understanding of the plant dynamics, but if you don't have the plant model, how do you tune then? And another issue, and that's not an exhaustive list but just some examples, another issue is that if you're targeting fixed point microcontroller like we started discussing here, you need to worry about discretization and sampling time and discretization and parameter values. So how do you effectively do that? So what I hope to show you is our answer to all these challenges, and to follow the challenges in a logical way, we'll follow this design V, where we'll go from left to right. We'll start with algorithm design. The challenges here is that you need to be able to specify different types of PID control easily, to find the best one that suits your needs. You also need to be able to specify ideal or parallel form. Some applications require one or the other. You need to be able to specify output saturation, so your controller never requests the actuator to achieve some unreasonable value. You need to be able to enable integrator anti-windup protection, and if you have several PID loops and you need to switch between them, you need to have the capability for bumpless control transfer. That's the capability where you minimize the transient as you switch from one PID loop to another. You can implement all these capabilities manually, but then iterating and switching between different designs becomes pretty painful. So you have a solution that makes it easier, and that solution is Simulink PID controller block. It lets you choose different types of PID controllers. It lets you specify parallel ideal form. It lets you easily specify output saturation limits, integrator windup, and enable tracking mode. Let me show you how it works. Let's go to MATLAB and open the engine model, which is very similar to the first one that we looked at, except that here it doesn't have PID controller block yet, because I want to show you how you can add it. Here in the Simulink library browser, you can find it under continuous sublibrary or discrete sublibrary. Grab the PID controller block from here, drag and drop it to your model, and connect it to the rest of your model. And you're all set. So now to configure this PID controller block, open the block dialog. Here you have a lot of different selections. You can select the type of PID controller. You can select the form. As you make changes here, the compensator formula is updated to show you the changes. You can tune the gains. We'll talk about that in a second. In the PID Advanced option, you can specify the limits. You can enable integrator anti-windup protection, and you can enable tracking mode for bumpless transfer. When you apply these changes, you can go to the block and look under block mask to see the actual implementation using the basic Simulink blocks. So there is no black magic here. You can actually see what we do to implement this logic. As you go back to the block dialog and disable or turn off some of these options, apply the changes, you can see how the implementation changes accordingly. So that's the simple PID controller, now very similar to what we saw in the Wikipedia picture. Let's now talk about tuning challenges. This is probably the most interesting step of the PID workflow. As I said, finding gain values is basically about meeting certain requirements, and the most common requirements or specifications are response time and stability, or overshoot, or phase margin if you're more familiar with control theory. And as I mentioned already, a lot of times people find these gain values by tuning on hardware. Manual tuning is time consuming, it's trial and error process, and you never know if you will end up with the optimal design. PID control became popular because people figured out some rule-based tuning methods, such as Ziegler-Nichols. Those have limitations too. They cannot be applied to some types of systems, for example open-loop unstable systems, and the design that you get cannot be easily fine-tuned. So for example, if you want to make it a little faster or slower, there is no easy way to do that. So we have a solution for that. Our solution is a special PID tuning algorithm and an app user interface that makes it easy to use this algorithm. The PID tuner that we offer automatically finds gain values to meet specifications. It provides easy fine-tuning capabilities by giving you just two simple sliders to use. And it supports all types of plans, stable or unstable, plans with time delay or with no time delay. PID Tuner ships in Simulink control design. Let me show you how it actually works. Let me switch back to this model. Let me go up, bring the scope. And instead of this default gain values, I'll parameterize my PID controller with variables kp, ki, kd, and n. I should say a couple of words about this variable n. You can see how it's used in the PID controller in this formula. It's all about the derivative term. When you differentiate the error signal, you don't want to differentiate it directly, because the error signal is just the set point minus measured plant output. And when you measure anything, there is always noise. And when you differentiate noise, you just amplify it. So the good way to implement the derivative term is to filter the noise with a low-pass filter and differentiate it then. And if you do that, you can actually avoid pure differentiation. So think about this term n as the bandwidth of the low-pass filter you use to filter the measured signal when you calculate the derivative. Anyway, just one of the parameters of the PID controller that you can tune. So now when we parameterize the PID controller with these variables, let me show you that I define their values in MATLAB workspace using the default values. So kp and ki are 1s and n is equal to 100. Let me also change the initial condition of the integrator to 9, because that value will let me start the simulation from steady state. I'll run the simulation, and with default gains we can see that design is unstable. We have a lot of oscillations and ringing in our controller. So we want to fix that. Open the PID controller block. Here we have the tune button. Let's press it. And what happens is that the PID tuner linearizes the Simulink model, linearizes the plant model that we have in Simulink, comes up with a transfer function describing the plant, and automatically finds PID gains that we can see here to give us this nice, stable, closed-loop step response. All we have to do now is update block parameters with tuned values. When we do that, let's click Apply here. Let's go to MATLAB for a second. We see that all the block parameters, all these variables, are updated. And if we go back to the Simulink model and run the simulation with the new values of the PID gains, we see that we have this very nice, stable, fast response that is much better than the original design. Now, the biggest challenge when you're tuning, probably the biggest challenge, is a situation when you don't know the dynamics of the plant. So in that case, the system that you're trying to control is just a black box. You don't know anything about what's happening inside. But what you can do is put some input signals through your engine, collect the output, and use that input-output data to get an understanding of engine dynamics. And we have a solution for that. In release 2014A, we integrated system identification capabilities right into the PID Tuner. Using those capabilities, you can import measured input-output data directly into the PID Tuner app and use that data to identify plant transfer function interactively or automatically. I will show you that in a second. And once the plant transfer function is identified, you can use it to automatically tune PID controller gains. So let me switch to MATLAB. Let me execute this script that loads input-output data and the time vector into MATLAB workspace. The data is plotted here. This is the throttle input signal that we put into the engine, and this is the actual measured engine speed. So again, if we didn't know anything about engine dynamics, we could put the throttle command to the engine, measure the engine speed, the output, and use this data to identify engine dynamics. Let's do that. To do that, we will launch PID Tuner by typing PID tool. We'll start by identifying a new plant. This opens a new tab called Plant Identification, and it tells us to specify the I/O data. In our case, we have step response, so click here. Specify the name of the output variable, output. Specify the parameters of the input step. The amplitude is 0.5. The initial value we can get from the first value of the input vector. The step happens at 2 seconds, and the sample time we can specify like this. Now we can import this data into the tool. The output is shown here in the green line, and the blue line shows the output of the transfer function that the tool is automatically trying to feed to this data. So as we see, it doesn't work so well, and the reason is that when we're doing this feeding, it helps if the output data starts from 0. So to do that, we'll pre-process the output data, we'll remove the offset from the output data, and we'll add the value of -2000 to have the output start from 0. So we'll click Update. So we see that now the output starts at 0. This is the input data. We're done with this task, pre-processing. And now the data that we will be trying to feed is shown by the green line, and the output of the model is shown by the blue line. And what this blue line shows is that we're trying to feed the transfer function so that when we put the measured input through that transfer function, the output of the transfer function shown by the blue curve matches what we observed in the actual data. Now we start with a first order transfer function that just has one pole. We can adjust the value of this pole interactively. We can also adjust the steady state gain. We can adjust the gain of the transfer function like that. So we can do interactive tuning, or we can do tuning automatically by pressing this button. and then the tool tries and goes to adjust those parameters to get the best fit. So it looks maybe decent, but maybe you can do better. So you can try using a different structure of the trans function, for example, a pair of underdamped poles. So let's select this structure. Again, we can do some tuning interactively, or we can again press this button and let the tool do the fitting for us. It takes a few iterations, and when it's done, it comes up with a pretty good fit. So let's save this plan for design. Let's just use this plan that we got now. It's called plant 1. Let's change the PID controller into PID with derivative filter. Here we can use the sliders to make the design a little faster or a little slower and a little more robust. Basically, this increases the face margin of the design, or a little more aggressive. So that's the sliders that I mentioned that give you the ability to easily fine-tune the design. So let's just go again with the default design. We'll export it to MATLAB workspace as a variable C. Do that. Close this tool. And now we have the PID variable C. And let's use the gains that we found to initialize the block parameters in Simulink. So we'll set KP to KP gain of the variable C, and we'll do the same with all the other gains. And the parameter n is just the inverse of the time constant of this object C. So now if I go back to Simulink, and we are in the situation now where we basically didn't use the inside of this block, the engine block. We just use input and output data to identify transfer function for this engine, and then we used that trans function to tune PID controller gains. But now, because we actually have this engine model, if I navigate here, we'll see that we have a lot of blocks. For example, if you go here, you will see that we have some nonlinear functions, some nonlinearities, and so on and so forth. We can actually try this PID controller that we designed using input-output data on this nonlinear model and see how it works. And as we see, it works pretty well. But the general workflow that I was trying to illustrate is that even if you don't have any knowledge about dynamics of the system, you could come up with PID gains by measuring the input and output data to the actual engine, identifying the trans function describing the engine, and using this trans function to come up with PID controller gains. Let's now talk about implementation challenges. Here you need to worry about discrete time design, scaling for fixed point processor, and generating efficient code. And our solution is PID controller blocks, the tuning algorithm, fixed point tool, and embedded coder. And so what I mean by that is that when you use PID controller block, you can easily switch from continuous time to discrete time implementation. In fact, you can start with discrete time implementation and tune the discrete time controller gains directly. As I already showed, PID controller block has data types tab that lets you set fixed point attributes, fixed point scaling for all the signals and parameters. And we have a tool, fixed point tool, which is part of the product called Fixed Point Designer, that lets you automatically set fixed point scaling using several different methods. And finally, this block supports code generation, so you can automatically generate compact, efficient code from the block. Let me switch to MATLAB. Let me open this model. In this model, we still have our PID controller. Let me open the block dialog. But in the data types tab, we specified fixed point data types. So you see the 16-bit fixed point data types for all the parameters and signals in this block, and we did the scaling automatically using fixed point tool. I don't have time to show how we actually did it, but we have other webinars showing you how to use this tool. As a result, if I run the simulation, let's go up and look at the scope, we still get this very nice performance. And what I can go and do now is automatically generate the code for this PID controller block using embedded coder. Again, there are other webinars that show how to configure automatic code generation, but I'll just very quickly generate the code for you. Let's set all these parameters as tunable. And generate code. And this is the code we just generated. So again, you see the gains and the algorithm itself. And now this code is ready for implementation on the processor. Let me talk about verification. Ultimately, you need to verify that whatever you design in Simulink will work on the actual hardware. It's also very helpful to be able to test your design before hardware prototypes are available, so you don't have to wait for them. And it's very helpful to test all sorts of corner cases. Now, all this can be done very well using nonlinear simulation. And that's what we've been doing. When we designed PID controller gains using linear control techniques, we tested our design in nonlinear simulation. And you can use nonlinear simulation to test different operating conditions. So instead of doing just a step change in reference speed from 2000 RPM to 22,000 RPM, we could do bigger transients or do transients at other operating conditions to check how our controller performs. We could also test different stages of design elaboration. So we started with a simple continuous time controller with double data types. We could test it in nonlinear simulation, but then we elaborated our design to do discrete time controller implementation with fixed point scaling, and we can test that in simulation as well to make sure it still works well. We can also generate the code from our PID controller, as I showed you, and then test this code using a technique called software-in-the-loop testing. This lets you run the C code that you generate from the block against the plant model in Simulink and verify that the code that you generated gives you exactly the same results as the PID controller block that you designed in Simulink. Again, there are other webinars showing how to do that. I also want to acknowledge that there are more challenges that people have to face when designing PID controllers. Oftentimes, simple single input, single output PID controller is not enough, and you have to deal with more complex architectures such as multi-loop and MIMO architectures, where there might be multiple PID controllers and maybe other blocks to tune, like this example where we have two PI controllers and a decoupling matrix to deal with this multi-input, multi-output distillation column plant. So in that case, people typically use tools like successive loop closure, which tunes one loop at a time, but those require a lot of time and experience, and again do not guarantee optimal results. I want to briefly mention here that we have a tool called Control System Tuner, which automatically tunes such complex controllers. With this tool, you specify blocks you want to tune, you select from a number of pre-canned requirements that we have for you, and then the tool automatically and quickly tunes block parameters to meet all the requirements. Using this tool, you can tune complex decentralized controller architectures like the one I just showed you on the previous slide. This tool is part of Robust Control Toolbox, and if you want to learn more, there are webinars and videos on Robust Control Toolbox page that shows this tool. Another practical consideration that almost everybody runs into is gain scheduling. If you're controlling a nonlinear plant like this engine that we're dealing with, most likely the dynamics of the engine changes quite a bit from low speed to high speed, and this is very common. So a common way to deal with that is do gain scheduling, when you schedule the gains with some operating variable, for example, engine speed. Our solution for that is to obtain a planned model for each operating condition using scripting capabilities of Simulink control design. With the scripting capabilities, instead of using the graphical user interface like I showed you, you can write a MATLAB script that will linearize Simulink model at different operating conditions, get a set of transfer functions, and then again, using a script, you can design a family of linear controllers at all these different operating conditions, and then schedule these controllers using lookup tables in Simulink. In fact, we have a whole webinar that talks about gain scheduling in Simulink, so if that's something of interest to you, I encourage you to watch that, and we also have a video on Simulink control design product page. So in summary, I gave you a sneak peek into a quick and simple workflow for design, tuning, and implementation of PID controllers in MATLAB and Simulink, and I showed you how PID controller blocks in Simulink and PID Tuner in Simulink control design, as well as the PID objects and the PID Tuner and control system toolbox help you address these challenges that we listed here. Now I understand that this was very fast and probably didn't go into enough detail to answer the questions you have lingering in the back of your mind. So I encourage you to contact us so that you can discuss your specific problem with our application engineers, who will be very excited to help you apply those tools to your specific problem. Last thing that I want to mention is that you can learn more by visiting the product pages that I discussed today. You can also watch other webinars listed here, and also watch videos available on all those product pages. And again, if you want help with your specific problem, please contact us and we'll be happy to talk to you.